Good morning, good evening, good afternoon, boys and girls. So, this is the lesson about quality of service QoS. We are going to go over some of the basics and foundations of quality of service, um, classification, marking, classification, marking, queuing, and policing. These are some of the concepts that we will go over it. So let's go ahead and start with the first one. And this is about what is QoS? What is quality of service? Quality of service provides the ability to assign a different priority to one or more types of traffic over others for different applications, data flows, or users so a certain level of performance can be guaranteed. QoS is used to manage contention for network resources for a better end user experience. In this chart, we have an example of quality of service. And basically, we have data, we have voice, and video. What information do we have for them? Well, when we are talking about data, we have smooth, bursty, benign, and greedy, drop insensitive, delay insensitive, and TCP retransmits. What about voice traffic? It is smooth, benign, drop sensitive, delay sensitive, and UDP priority. And finally, we have video, where this type of traffic can be bursty, greedy, drop sensitive, and UDP priority. So, depending on the customer needs, we can establish a different set of rules or filters to prioritize different kinds of traffic. And this is figure 16.1. It shows the different traffic characteristics for data, voice, and video. Let's go ahead and clear this board and let's continue moving forward. And what about quality of services for data, voice, and other services? Well, basically, it will depend on the filters that we apply and the different rules that we apply for data, voice, and video. And these are the voice requirements for one-way traffic. For example, latency of less than or equal to 100 milliseconds, jitter of less than or equal to 30 milliseconds, loss of less than or equal to 1% of bandwidth only in 128 kbps. We're talking about voice requirements in a one-way traffic, okay? So we're referring to this one over here. What else are we missing here? There is quite a variety of video traffic types around today on the internet, Netflix, Hulu, and other applications. Gaming and remote collaboration requires streaming video, real-time interactive video, and video conferencing. Video requirements for one-way traffic are latency of less than or equal to 200 to 400 milliseconds, jitter of less than or equal to 30 to 50 milliseconds, loss of less than or equal to 0.1 to 1%, bandwidth of 384 kbps to 20 mbps or greater. And these are just some examples of the different rules and filters that we can apply to different kind of traffic per se, even if we are working with data, with voice, with video, Over here, we have the data over there and some of the voice traffic over here for telephones. So that's basically a brief example of some of the characteristics that we need in order to apply different filters. Let's clear the board and continue learning about these concepts. And now we have the trust boundary. Trust boundary refers to a point in the network where packet markings aren't necessarily trusted and is where we can create, remove, rewrite. It means rewrite markings. The borders of a trust domain are the network locations where packet markings are accepted and acted upon. Figure 16.2 that we are seeing right now shows typical trust boundaries. And these are just some examples of trust boundaries that we have for routers, switches, integration to IP services, and integration with the internet service provider. Okay, let's continue learning about them. In the previous figure, we have some IP phones and routers interfaces that are typically trusted, but not beyond certain point. Those points are trust boundaries. Let's just return for a moment and let's validate where do we have the trust boundaries. Here, between the phones and the switches, and here between some of the routers and switches, all of them are trust boundaries. And that's basically what I want you to know for now. To meet the exam objective, understand these three things. Untrusted domain. This is the part of the network you're not actively managing, populated by PCs, printers, etc. Trusted domain. This is the part of the network with only administrator managed devices like switches, routers, etc. And trusted boundary, where packets are classified and marked in an enterprise campus network. The trust boundary is almost always at the edge switch. So, what do we have here? Let me just return because I changed the slide by mistake. So traffic, and that's where I was trying to get there, but for some reason I lost track of that. Give me just a moment, please. Okay, so traffic at the trust boundary is classified and marked before being forwarded to the trusted domain. Marking on traffic coming from an untrusted domain are usually ignored to prevent end-user control markings from taking unfair advantage of the network QoS configuration. Next, we're going to go over in the next section or chapter, we are going to explore the following mechanisms: classification and marking tools, policy shaping and remarking tools, congestion management or scheduling tools, link-specific tools. Okay, let's go. What do we have here? In this slide, we have classification, marking, policy and selective dropping, queuing, we have scheduling and mapping, we have the ingress, and we have the egress. So classification, what is the definition for it? A classifier inspects packet fields to identify that traffic type. The purpose determines which traffic class a packet belongs to and how it should be treated. The next step, classified traffic, is sent to policy enforcement mechanisms, e.g., policy shaping. Classification should not be a constant cycle. It consumes time and resources. Policy enforcement mechanisms, marking, tagging traffic for prioritization, queuing, organizing packets into queuing by priority, policing, enforcing traffic, rate limits, routing and remarking excess traffic. So we're talking right now about the policy enforcement mechanism marking, and we're talking about tagging traffic for prioritization. Policing is basically enforcing traffic rate limits, dropping and remarking excess traffic. Queuing is organizing packets into queues by priority. And finally, shaping is buffering, delaying traffic to fit bandwidth constraints. Marking techniques by layer technology, layer 2 Ethernet wire or class of service located in 802.1q VLAN tag. It uses 3-bit priority code point (PCP) field. It defines priority levels of Ethernet frames. Then we have layer 3 IPv4, IPv6. Those are the IP type of service, TOS or TOS. IPv4, 8 bits with 3-bit use as IP precedence. IPv6 equivalent field is traffic class. Differentiated Service Code Point, DSCP. Modern method for packet marking is this one uses 5 bits with the 8 bits differentiated services DS field in the IP header, allowing the creation of traffic classes for prioritization backwards compatible with IP precedence. Most widely deployed marking methods end-to-end significance. Class selector, we're talking about a subset of DSCP values. In fact, in one of the following labs, we are going to learn about this field and the way it works in the simulation of the packet tracer lab. So we will cover that later in the practice. It uses the same 3 bits as IP precedence, wireless 802.11, traffic identifier TID, 3 bit field in the QoS control field, similar to QoF, but specified to wireless frames. Quick comparison. QoS is actually wired or Ethernet, and TID is wireless. Okay, with this brief explanation, what we have is the ingress traffic, the classifying, that is number 1. Then we have number 2 for the marking. We have number 3 for the policing and selective dropping. Number 4 for queuing. And number 5 for scheduling and shaping. Then we have the egress. We have ingress and egress at the end. If we want to do a better division and a more briefly description of them, we can divide it in a total of 3. Classification and marking, congestion and avoidance, and congestion management. With that being said, those are the steps for QoS classification and marking. Let's continue learning about quality of service. In this one, we have policers, drop remarks traffics, shapers, buffers, delays traffic, and the administration of the congestion control. And you can see some of the traffic filtering and shaping that we are doing in order to prioritize traffic correctly, depending in what we need. Okay, so let's start with polyzers. Since polyzers make instance decision, you want to deploy on the ingress if possible. You want to drop traffic as soon as you receive it, it is going to be dropped anyway, right? Still, you can place polyzers on an egress to control the amount of traffic per class. When that traffic is exceeded, polyzers don't delete it by introducing jitter or delay. They just check the traffic, drop or remark it. Just know that due to the higher drop probability, you can end up with a whole bunch of TCP resends. Shapers are usually deployed between an enterprise network and the ISPs, Internet Service Providers, on the egress side to make sure you stay within the contract rate. If the rate is exceeded, it gets policed by the provider and drop. This allows the traffic to meet the Service Level Agreement (SLA). Shaping introduces jitter and delay and result in fewer TCP resends than polyzers. Tools for managing congestion. We have the inbound packets, then it comes number one. Number one is the inbound packet, number two is the queuing. Then we have that packets are assigned to various queues when the congestion output interface is congested. So packets are assigned to various queues when the output interface is congested. Then we have number three, which is the scheduling. And finally, output packets. That is number four. So this is a little bit of the way that we have the administration of incoming packets, then the queuing, then packets being assigned to various queues when the output interface is congested. Also, the priorities are added to those specific packets depending on the customer needs. Then we have the scheduling and the output packets. That's basically the process. Next, we already went over this slide and we already explained it. So let me see if there is more important stuff we are missing here. Basically, the definition of queuing or buffering. Buffering is the logic of ordering packets in output buffers and is only activated when congestion occurs. When the queues fill up, packets can be reordered so that the higher priority ones are sent out of the exit interface sooner than the lower priority traffic. Scheduling. This is part this part of the process is when we are deciding which packet should be sent out next, and of course whether or not there is congestion on the link. Make sure you're familiar with these three scheduling mechanisms. So we're talking about queuing, buffering, and scheduling. But in this case, queuing and buffering is pretty much the same. And then we have scheduling. Now, if we want to divide these in three mechanisms, we can say we have the queuing, then we have the filters added to the packets, and they're being to assign to specific interfaces depending on priorities. That is number two. And then after the filters, we have the scheduling of the packets. Remembering we always have the input packets, and at the end we have the output packets. That's basically the way that congestion management works. Great. With that being clear, let's continue moving on. And we got pretty much the same image, but there are some more concepts that we are still missing, and these are very important in this case. First, In, first out, FIFO, a single queue with packets being processed in the exact order they arrive. Priority queuing, PQ. So let's just write it right there so we can remember it. The first one that we have is first in, first out. And that is actually FIFO. Do you guys remember what it stands for? Is a single queue with packets being processed in the exact order they arrive in. The second one is priority. Priority. Priority queuing. And if you want to take notes, it is actually recommended. So you remember about these concepts. Similar to round robin scheduling, lower priority queues are only severe when the higher priority queues are empty. There are only 4 queues and low priority traffic may never be sent. That is number one, the FIFO. Then number two, we have the PQ. And then let's continue moving forward with number three. What do you think we have here for number three? We have CQ, custom queuing. Okay, now I might spell something wrong here, so let me just validate it. This UE is Q, actually queuing. It is like this. So let me just copy this in the other place so I don't miss it. And this will be CQ, CQ, right? With up to 16 queues and round robin scheduling, CQ prevents low level queue starvation and gives us traffic guarantees, but it doesn't provide strict priority for real-time traffic. So void traffic could still end up being dropped. And finally, we have number four, which is weighted. That is weighted for queuing. That is queuing. Maybe there is some misspelling there, but let's just ignore it for now. That is WFQ. And what is the description for this one? WFQ is the Cisco default queuing mechanism. WFQ is actually a pretty popular way of queuing for a long time because it divided up the bandwidth by the number of flows. This provided bandwidth for all applications and worked great for real-time traffic, but they there weren't any guarantees of particular flows. So let me just fix this word for queuing because I think I've been spelling this one all along wrong. So I'm trying to fix the spelling now. It looks a little bit more like it. So what I'm trying to do is fix the spelling. Maybe I'm doing something wrong here. So I'm trying to fix that spelling. Queuing. Queuing. That one is actually FIFO, PQ, CQ, and WFQ. Okay, so I am just fixing the spelling in my presentation as well, so I don't have those errors there any longer. Yeah, that's pretty much it. Those are the queuing methods that we currently have. Um, FIFO, PQ, CQ, and WFQ. Those are the ones we have. Let's continue learning about them. Okay, when we're talking about modern queuing, CVWFQ, we are talking about bandwidth fairness, no latency guaranteed. LLQ it prioritizes real-time traffic. So the first one is called class-based weighted fair queuing. It's actually CBWFQ, and it provides fairness and bandwidth guarantees for all traffic, but it doesn't provide any latency guarantee. It typically only used for data traffic management. Low latency queuing, LLQ. LLQ is really the same thing as CBWFQ, but with stricter priorities for real-time traffic. LLQ is great for both data and real-time traffic because it provides both latency and bandwidth guarantees. And this is not going to look fine because I need to clear the board. So let me just clear the drawings. And now I can explain you guys a little bit about how this one works. So we have the incoming packets, that's the ingress traffic, and we have the LLQ and the CVWFQ. Remembering the first one over there is basically doing the function of prioritizing real-time traffic. And the second one is bandwidth fairness, no latency guarantee. Then we have the scheduler over there with the integration of priorities and packets. And finally, we have the TX ring and the packets out. And we are talking about egress. Egress. So that action is egressing traffic at the end of all the priority filters and rules that were previously applied. Let's continue learning about these topics. So let me just clear the board for a moment, and hopefully I will be able to change this. But for some reason, the presentation is kind of stuck. So let me just close everything and open it again. And let me just return to that 15 slide where I was. For some reason, it's not coming up. So let me pause the recording so I can fix this. Okay, now finally we have it. Figure 16.7 shows how congestion avoidance works. And here, this is what we have. We have the three traffic flows. It basically they start at different times, and we have the tail drop, another traffic flow that start at this point. All TCP flows synchronize in waves, leaving much of the available bandwidth use. And then the time that is being utilized in this example. So what do we see in this specific figure? We can see three traffic flows beginning at at different times, resulting in congestion. In a situation like this, you know that TCP may cause tail drop because it drops the traffic as soon as it's received. If the buffers are full at that point, TCP could begin another traffic flow, synchronizing the TCP flows in waves, which sadly leaves much of the bandwidth unused. Okay, great. Let's continue learning about quality of service, and let me just clear the board for a moment. And let's see if I can continue learning about this. There is a problem with the presentation, so I'm just going to use the other version that I have. I'm just going to open the PDF file in that version. So give me just a moment so I can work on it. We don't get too complicated on this. So we were working along with one of the last sections is actually 16, and we were explaining about this. We were explaining about the traffic, the integration of the avoidance of traffic. What do we have here is the important and essential part. Okay, give me just a moment so I can work on this. Mm, okay, so in this page, we have pretty much the same that we explained before, but we have a deeper explanation of tools for congestion avoidance. We're talking about background, TCP, and flow control. And revolutionize flow control by allowing a receiver to regulate how much data the sender could transmit. It replaced methods like example TCP pre-sliding windowing SPX that cut transmission rates in half and kept them low in for the entire connection. Some of the improvements that we have in this section is that TCP reduces the transmission rate when congestion occurs, but increases it again once missing segments are resolved or acknowledged are received more efficient than older methods, but not perfect. So we are talking about TCP and flow control on that one. What about problems with the arise? We are talking about tail drop. It occurs when packets are dropped because the receiving queue is completely full. Wait, wait test. It wastes bandwidth. So we are throwing bandwidth to the trash, basically, in an easy way to explain it. It wasted bandwidth because TCP transmits repeatedly on, until acknowledged are received. TCP global synchronization happens when multiple TCP senders simultaneously reduce their transmission rate after packet loss, leads to inefficient bandwidth utilization and oscillations in throughput. What about congestion avoidance mechanism? Instead of waiting for queuing to fill completely, packets are dropped early to avoid tail drop. Jobs are based on traffic weight, not randomness. Physical key mechanism, weighted, random, early detection, WRET, a congestion avoidance method that drops packets before queues overflow, uses traffic precedence priority weights to decide which packets are dropped, ensures high priority traffic, e.g., VoIP, experiences lower loss rates than less important traffic, example, social media browsing, and it balances efficiency and fairness during congestion. So the last two that we were talking about for tools for congestion avoidance, we have the problems that arise and the congestion avoidance mechanisms. And we were talking about, for example, tail drop, TCP global synchronization, weighted random early detection mechanism. Those are some of the tools for congestion avoidance, sliding windowing, in TCP improvement. That's basically what we were trying to fully understand. What about this one? It's pretty much the same one. Do we have more concepts? Okay, this is just a summary what we covered earlier, and here in the congestion avoidance figure 16.7, we can see three traffic flows beginning in at different times, reducing in congestion. In a situation like this, you know that TCP may cause tail drop because it drops the traffic as soon as it receives if receive it, if the buffers are full. At this point, at that specific point, TCP would begin another traffic flow, synchronizing the TCP flows in waves, which sadly leaves much of the bandwidth unused. Let's learn about MBAR and what is this one. So maybe I can improve this. Great. What is the definition of MBAR and how does it work? We have priorities. In this case, we have a higher priority, a medium priority, and a low priority. All communication has access to the media. That higher priority communication has a greater percentage of packets. We have voice over IP, financial transactions, and web page traffic. Network-based application recognition (NVAR) enables deep packet inspection from layer 7 to layer 4 to layer 7 to classify applications. It works in passive mode, statistics, or active mode marking for QoS. Let's go ahead and clear the board and see if we can continue moving forward. Let me close this for a moment. And that's pretty much the presentation. The last part that we have here is a summary of some of the concepts that we have gone over them. We have covered pretty much classification and identified classification, the labels and marking, the policing and enforcement, and administration for congestion with the queuing. At this moment, we have covered pretty much 90 to 95% of most of the topics that are going to be on the CCNA certification exam. So we are pretty much in with a good course of action. So boys and girls, I want to see you at the top of success. Remember, practice makes perfect and take care. I will see you on the next class. We will be doing some of these in Packet Tracer with simulations and show commands and adding commands to the routers and learning about quality of services in a real life environment or a simulated live environment with Packet Tracer. So until next lesson, take care. I see you around.